All right, so we're going to finish chapter 10 today. You guys have quiz tomorrow on chapter 10, and then we're also going to be starting the last chapter on permutations and combinations. Remember, Friday, June 9th, last day to hand in any missed assignments. After that, they go in as zeros and your mark will go down. So even though Friday is a PD day, you can still email me stuff. I can print it off and mark it. Yes, sir. Where is it? In locker? Okay, cool. All right, so we touched briefly on composition of functions on Friday. The composition of f at x and g at x is defined as f at g at x. It is formed when the equation g at x is substituted into the equation of f at x. It exists only for those x's in the domain of g for which g at x is in the domain of f. So again, that is read as f o g at x, or f of g of x, or f composed with g. Another way of writing it is with the little circle in between the f and the g. So don't confuse that with timesing, multiplication. That's an open circle. As it says there, it must not be confused with multiplication. F O G at x does not mean f times g at x. So if f at x is the root of x and g at x equals 2x minus 3, then the composition of f at x and g at x is f at g at x. So g is embedded into f. Wherever we see the variable in f, which is under the radical, we replace it with what g is. So the x is replaced with what g is, the 2x minus 3, and what happened to the x before, which in this case is under the radical, also happens to the 2x minus 3. So when you do these, you work from the inside out. Order is important. F at g at x is normally not the same as g at f at x. F at g at x means substituting g into f. On the other hand, g at f at x means you're substituting f into g. So order matters. You always work from the inside out. The first example says f at x is 4x, g at x is x plus 6, and h at x is x squared. Determine each value. So for question A, you want to find f at g at 3. You work from the inside out. You find g at 3 first. And to do that, you have to use the g at x function. G at 3 is x plus, or g at x is x plus 6. So g at 3 will be found by letting x equal 3 in x plus 6. So that gives you 9. And now you're going to find f at 9. Now you're using the f at x function. And f at x is 4 times x. So 4 times 9 is 36. There's the value of f at g at 3. Again, work from the inside out. Question B, g at h at negative 2, working from the inside out, we first find h at negative 2. So h at x is x squared. All of x is squared, so all of negative 2 is squared. That gives us 4. And now we want to find g at 4. So we have to use the g at x function, which is x plus 6, but now x is 4. And so that gives us a value of 10. H at 2. Again, working from the inside out, you're going to use the h at x function twice. H at x is defined by x squared, so when you square 2, you'll get 4. And then you have to use h at x a second time. Now you're squaring 4, gives you a value of 16. And the last one, again, working from the inside out, we first find f at negative 3 using the f at x function. You get negative 12, and now you do h at negative 12. So now we have to use the h at x function, which again is x squared. All of negative 12 is squared, gives you positive 144. Right? So sometimes you're going to be getting an actual numerical value for these because you're given a specific number that the variable equals. Sometimes, though, your composition of functions will involve an expression because you're not asked to find for a certain value of x. Like these ones here, determine FOG at x. So again, that means f at g at x. So g is embedded into f. Wherever we see the variable in f, we replace it with all of g. And what happened to f before, which was everything's under the radical, will also happen to our new function. But again, the variable in f is replaced with g, which is just x squared. Whatever happened before also happens to this new function. Right? You're subtracting 1 and it's all under the radical. So what about the domain and range of this? Well, you could use your graphing calculator if you wanted to help you get that. You could put that equation in there. Y equals the root of x squared minus 1 . Let's set our windows to their standard setting, zoom 6. That's what it looks like. Okay, it looks like it starts at positive 1 and negative 1. If we let x equal 1, yep, that's where it starts on the right. At that point, y is 0. If we let x equal negative 1, that's where it starts on the left. And again, the y is 0. But here's where that comes from. If you look at the expression, the root of x squared minus 1, you cannot take the root of a negative number. X squared minus 1 has to be greater than or equal to 0. This is where the restrictions come from. This is where we get our domain from. Now, because it's x squared minus 1, it's a little difficult to solve for x, get x by itself when you have an inequality. The way we've handled these in the past is we've drawn a graph of y equals x squared minus 1. That is a graph of y equals x squared shifted down 1 unit. Its vertex will be at 0, comma, negative 1. You can find the x-intercept for x squared minus 1 equals 0 by solving for x. So x squared will equal 1 and x will equal plus and minus 1. There's where those plus and minus 1 numbers come from. That's where the graph starts. Those are the x-intercepts. And the graph goes upwards and to the right from positive 1 upwards and to the left from negative 1. That is the graph of the square root of x squared minus 1. And actually, I'm going to back up here. I was graphing not the square root of x squared minus 1, but just x squared minus 1. This is the graph of x squared minus 1, and it must be greater than or equal to 0. That means the graph must be above the x-axis. So we're looking at this portion of the graph and this portion of the graph. That's what we're looking at. And that's why the domain is x must be less than or equal to negative 1, greater than or equal to positive 1. We can use interval notation from negative infinity to negative 1 and from positive infinity, that's backwards, positive 1 to positive infinity. We always go smallest to greatest. And we'd have square brackets on the negative 1 and the positive 1. Because x squared minus 1 can equal 0, you can take the square root of 0. You just can't take the root of a negative number. So that's where the domain comes from. And the range is y is greater than or equal to 0. We saw that when we actually graphed the root of x squared minus 1. Okay, which is on our graphing calculator. We're finding the domain and range of that graph but we use this graph over here to get our domain. Then we want to find GOF at X. So now F is embedded into G. So F is embedded into G. So you're going to take all of F, the root of X minus 1, and replace that into the variable on G. So you're going to have the root of X minus 1, and whatever happened to the G before, which is that's all squared, is now going to happen to this. And the square root and square cancel each other out, and we get X minus 1. Now, this is a linear function. Normally the domain of that is all real numbers. However, when we're looking at restrictions, we have to look at the original expression. So because the original expression has the root of X minus 1, once again, X minus 1 has to be greater than or equal to 0. And because this one is not a quadratic, we can get X by itself. X must be greater than or equal to positive 1. That's our domain. And to see that on the calculator, again, we would have to put the expression in, the original expression, the root of X minus 1 all squared. When we graph it, this graph starts at positive 1. And you can see that Y starts at 0. And again, if you let X equal positive 1, that's the minimum number that X can be. If you let X equal positive 1 in this expression, 1 minus 1 is 0. The root of 0 is still 0. So that's why the graph starts at the point 1 comma 0. So our domain is from positive 1 to positive infinity. Our range will be from 0 to positive infinity. Right? So there's that one. The last one, we want to find FOG at H at X. So F at G at H at X. So again, working from the inside out, we would first embed H into G. So H is 2x plus 3, and that's embedded into G, which means it's squared. Let me write this out here. So we'll start with first G at H at X. That's our first step. So H is embedded into G. H is 2x plus 3, and that's embedded into G, which is x squared. So now the 2x plus 3 needs to be all squared, which we can multiply that out, FOIL that out, and get 4x squared plus 12x plus 9. And now we will do f at g at h at x, which means that what expression we just got is embedded into f. The f function is the root of x minus 1. So the variable there is replaced with 4x squared plus 12x plus 9. So that is replacing the x with our expression from before. But we can't forget about the fact that f at x is the root of x minus 1. So we have to have a minus 1 on the end there. So when we simplify this, it'll be 4x squared plus 12x plus 8. There's our final expression. And in this case, it doesn't ask us to find the domain and range, but if it did, we could use our calculator. Also, I think, remember the radical part has to be greater than or equal to 0. So 4x squared plus 12x plus 8 has to be greater than or equal to 0. We can factor this by taking out a common factor of 4. And remember, because this is a quadratic, we would look at the graph of this function. This is a quadratic that opens upwards. We can find our x-intercepts by factoring that quadratic. That tells us our x-intercepts where y is 0. The factors there are x plus 2, x plus 1, which means that this quadratic has x-intercepts at -2 and -1. This quadratic opens upwards because the initial term is positive. Again, we want to know where this quadratic is greater than or equal to 0, meaning above or on the x-axis. That would be where x is less than or equal to -2, greater than or equal to -1. That's our domain. From -infinity to -2, and from -1 to positive infinity. The minimum value of this function will be when x is 0. I'm sorry, -2 and -1. You can also use your graphing calculator to help. Right, that equation, we'll put it in the square root, try that again, the square root of 4x squared plus 12x plus 8. And even though the calculator doesn't look like it hits the x-axis, it does, because if you go into the trace mode and let x equal -1, you do get a y value of 0. Same thing by letting x equal -2, you get a y value of 0. This also tells us that our range is that y must be greater than or equal to 0. It starts on the x-axis and goes upwards forever on both sides. Right? Number 3, you're given f and g. You want to determine g at f at x. Graph its state, domain, and range. So f is embedded into g. F, which is x plus 1, will be replaced into the variable of g. So x is replaced with x plus 1, and whatever happened to the x before happens to the x plus 1, meaning that it's squared and then decreased by 2. You might remember from 20-1 when you learned about quadratic functions, this is the vertex form of the quadratic. Right? Our initial term coefficient is +1. There's no number in front of the bracket, which means that the initial term coefficient is +1. That means the graph opens upwards. And again, remember the vertex is at P comma Q. Because the vertex form of a quadratic is y equals a bracket x minus p all squared plus q. We learned about this in 20-1, where the vertex is at P comma Q. So just like when we talked about our h value with transformations, the value of h is always the opposite of what it appears to be. In this case, the value of p will be the opposite of what it appears to be, because the general equation already has the minus sign there. And the only reason I'm talking about this is because this is the form that this equation is in. It makes it easy to graph. The vertex is at -1, -2, and it opens upwards. We could certainly generate or find Another couple points, we could find our y-intercept by letting x equal 0. So if you take that equation and let x equal 0, 0 plus 1 is 1, squared is still 1, take away 2 is negative 1. So there's the y-intercept. Also remember that quadratics have an axis of symmetry. It's a vertical line that goes through the vertex where the graph is symmetrical about that line, meaning that this y-intercept we found, which is 1 unit to the right of the axis of symmetry at a height of negative 1, there will be a corresponding point the same distance away from the axis of symmetry, just on the other side. So this gives us a couple points with which we can sketch the graph. If we really wanted to find the x-intercepts, we could by letting it equal 0 and then solving for x. They're going to be irrational numbers, but you could find them. Now that we have the graph, we can state the domain and range. There are no restrictions on what x can or not be. But this graph has a minimum point. It starts where y is negative 2 and goes upwards from there. So from negative 2 to positive infinity. That's our range. Okay. So same thing with this one. We're given f and g. You want to determine f at g at x, graph at state, domain, and range. So g is embedded into f. G is 3x plus 1. That replaces the variable x in f. But then you still have the minus 1 that is after the x in f. And so that'll give us the root of 3x. So remember from chapter 2, we talked about radical functions. This would be the graph of y equals the root of x with a b value of 3, means it's horizontally stretched by a third. But we can generate a few points quite easily just by choosing some specific values of x. For example, when x is 0, 3 times 0 is 0. The root of that is still 0. I'm going to jump to x equaling 3. When x is 3, 3 times 3 is 9, and the root of that is also 3. So this gives us a couple points. Remember that these graphs are curves, and you could definitely generate more points if you wanted to, but it would look something like that. So the domain will go from 0 to positive infinity, right? This graph starts at 0, 0 and goes to the right forever, as it's also going upwards forever. In this case, the domain and range are the same things. They're both greater than or equal to 0. Number 5 says, if h at x is f at g at x, then determine f at x and g at x. And maybe determine isn't the right word there, because there's really not any work that you can show to get this. Is more or less just done by inspection. If you look at h, which is composed of f at g at x, that means g is embedded into f. And if you look at what h is, there are two terms that involve the x minus 2. So we could say that g at x equals x minus 2. And if that is embedded into f to give us h, we could say that f at x is x squared plus x plus 1. If you take g and you embed it into f, you'll get h. I'm sorry, I wrote x minus 1 there. I should have written x minus 2. Apologize for that. Because that's what is repeating there. So again, this basically is just done by inspection. Same thing with question B. You're given H, you want to state what G and F could be, remembering that G is embedded into F. So there's going to be a couple different expressions that would work for this one. You could say that G at X equals X cubed plus 1. That's what's under the radical. And then F at X, we could say, is the root of X. If you embed G into F, if you replace the X and F with G, you get H. So that's one possibility. Here's another one though. We could say that G at X equals X cubed, and therefore F at X would be the root of X plus 1. If you take G and embed it into F, you replace the variable in F, replace that X with G, you'll get the root of X cubed plus 1, which is what H is. So both of these answers would work. And again, there's not really any work that you can show to get them. It's just basically doing a by inspection. So a few more examples. You're asked to, given F and G, find G O F at X, which is G at F at X. F is embedded into G. So F, which is X minus 1, the root of X minus 1, I should say, is embedded into G. But when we look at G, because there's no brackets around the negative X, this tells us that only the X is squared, not the negative sign. So when we embed F into G, only the root of X minus 1 would be squared. Now you can simplify this. Square root and square cancel each other out. But you still have that negative sign in front, which is like multiplying everything by negative 1. So there would be our simplified expression for GOF at X. Our simplified expression is a line, and normally a line has no restrictions on X or Y. But remember, to get our restrictions, we have to look at the original expression. The root of X minus 1 is where we're going to get our domain. X minus 1, which is under the radical, must be greater than or equal to 0. So therefore, X has to be greater than or equal to 1. This is where we get our domain from. From 1 to positive infinity. Now, because of this negative sign in front, remember that causes a reflection over the x-axis. Instead of going upwards, this one, I think, is going to go downwards, which we can confirm by putting it into our graphing calculator. Again, the original expression, negative, and then we'll take our square root of X minus 1. And notice we're not using any brackets there. Because only the radical part is squared, not the negative. So when we hit graph, this graph goes downwards. It was reflected over the x-axis. That's the effect of that negative sign in front of the radical. So our range will be from negative infinity to 0. Remember, it's always smallest to greatest. 0 is included, but the negative infinity is not. Okay? So use the graphing calculator. Another one where we need to determine F and G. If we look at what H is, we see that the cube root of X, there are two terms that have that in it. So if G is embedded into F, we could say that G at X is the cube root of X. And then F would have to be x plus 3 over 3 plus x. If you embed g into f, if you replace the x's with the cube root of x, you will get h. So that is one possibility for g and f. Probably the most straightforward one. There may be others, but this one's pretty straightforward. So in this case, f is the absolute value of x, g is x plus 1. Again, we want to do the embedded function f at g at x. Working from the inside out, g is embedded into f. Replace the variable in f with all of g, and you're going to get the absolute value of x plus 1. Remember that absolute value graphs basically are a V shape. This is the graph of the absolute value of 1 shifted, the absolute value of x shifted 1 to the left. Right? That 1 is tied to the h value. Whatever happens to the x happens to the x minus h, in this case, inside the absolute value. And the value of h is always the opposite of what it appears to be. So here, h would equal -1. This is the graph of the absolute value of 1 shifted 1 to the left. You might remember that the absolute value of x started at 0, 0, but we got to shift 1 to the left. The absolute value of x goes to the point 1, 1, 1 to the left. 2, 2, 1 to the left. -1, 1, 1 to the left. -2, 2, 1 to the left. Here's our graph. Okay, there's our graph. And so the domain would be all real numbers. And it goes left and right forever. But there are restrictions on why this graph starts at 0, 0 and goes upwards forever. So from 0 up to positive infinity. Okay, let's look at a couple application problems. A spherical weather balloon is being inflated. The balloon's radius, r, in feet, after t minutes is given by r equals the root of t. Express the volume of the balloon as a function of time. So to do this, you have to know what the formula for the volume of a sphere is. The volume of a sphere is 4/3 pi r cubed. A sphere is ball, basically. Okay? A basketball is a sphere. That's the formula for volume, but that is the formula for volume in terms of r. So if we were using function notation, we would say v at r. The volume as a function of r, the radius. But we want to write the equation as a function of time. So to do that, we are told that r equals the root of t. So what we would do is we would find v at r at t. We would embed r into v. R is the root of t. And our original equation for volume tells us that the r is cubed, so the root of t must also be cubed. So there's our expression. Now you could write that as t to the power 3/2. But because part B asks us to find the volume, or excuse me, the time, when the volume will be 4,000 cubic feet, I will leave my expression the way it is. Our volume is 4,000 cubic feet. We want to know what value of t will give us that. And actually, I think looking at this now, I will change it to power 3/2 because we want to solve for t. My first step would be going to the graphing calculator and going 4,000 divided by 4 pi. And I need to put the 4 pi in brackets. You could definitely do it in 2 steps if you want to, divide by 4 first and then by pi second. But if you do it in 1 step, you got to put the 4 pi in brackets so it keeps them both in the denominator. And this will give us an expression for t cubed, or t to the power 3 halves. It's approximately 318.31. And remember when we solve exponential equations, to get t to be t to the 1, we raise both sides to the power. That's the reciprocal. The reciprocal of 3 halves is 2/3. Because when you multiply the exponents on the left, you're going to get 6 over 6, which is 1. It gives you t to the 1, or just t equals. And power 2/3 on the right means the cube root of that number squared. And because we have that number in our calculator, we're going to keep it in there to give us the most accurate answer. So I'll start with the cube root first. Math, number 4 in the list is cube root of the previous answer. That needs to be squared. You can square first, cube root after, that's fine. Doesn't matter. Oh, I'm sorry. Oh, no, I did that right. Cube root and then squared. Oh, I did do something wrong. 4/3. So I apologize for that. So it's 4,000 divided by, in brackets, 4 pi over 3. Again, I put that 4 pi over 3 in brackets. Now we got it. 954.93. And that's the number that we have to take the cube root of and square it. So math 4 for the cube root of the previous answer squared. There we go. Approximately 96.97 minutes. Doesn't tell us what to round it to, so I just round it to the nearest hundredth of a minute. Okay. This next one, we're still dealing with the same scenario. A spherical weather balloon is blown up. Again, the radius in feet is given by r at t equals the root of t. This one asks us to express the surface area of the balloon as a function of time. So we need the formula for surface area of a sphere, which is 4 pi r squared. And if you needed any of these for a quiz or a test, you'd be given those. You don't need to memorize these. But part A asks us to express the surface area in terms of t. So surface area in terms of t means we can't have the variable r, we have to have the variable t. But we are told that the radius is the root of t. And because in the surface area formula the radius is squared, now the root of t will be squared. And in this case, the square and square root cancel each other out. And there's your formula for surface area in terms of t, the time. Part B wants to know after how many minutes will their surface area be 180 square feet. So 180 will equal 4 pi t. And in this case, we'll just divide both sides by 4 pi. And again, we want to put that 4 pi in brackets. So approximately 14.32 minutes. So on page 507, questions 1 through 4 and 6, you should work on those for practice. I'll post the solutions to Google Classroom. And remember, tomorrow we have our quiz for chapter 10, then we start in chapter 11. And that is the last chapter. So after that, we'll be reviewing for the diploma exam.